I love integers. Integers are great. Whole numbers, brilliant. They can go negative, they can go positive. You can do a lot of cool stuff with that. But also, sometimes you need those numbers that are in between the integers, you know? That's where all of the interesting things really happen. So typically what we do is we turn to floating point, right? Floating point is a standard, we all know it, IEEE 754. But, right, they're great. They're awesome. They're in every programming language ever made, right? You've got double precision, you've got single precision. But there are some issues with floating point. So many people know this, right? If you try to add 0.1 plus 0.2, you don't get 0.3. I don't really see that as an issue, right? For me, that's not the problem. The problem is that floating point is quite a complicated beast under the hood, right? You probably haven't thought that much about it, but it's actually quite complicated under the hood. The representation of the numbers is relatively complicated. There are a bunch of edge cases. Most importantly, you sort of need specialized hardware in order to actually perform the calculations. If you don't have that specialized hardware in the form of a floating point unit embedded inside your CPU, or externally if we're talking about the good old days, then you're going to do those calculations really slowly because you're going to have to do them in software, and it's really like debilitatingly slow. Now, let's say basically every modern computer, x86 based or ARM or whatever, the thing that you're watching this on now, it has a floating point unit. But there are many devices that use these kind of little chips in the world, and often in these kind of chips, they don't have floating point units, right? They don't actually have this acceleration hardware in order to do the calculations. Or if they do, it's not as powerful and it still takes a while to sort of crunch the numbers. So that can be a problem. That can be an issue. Or it cannot be. I mean, it depends. But often if we're working on these kind of devices, we sort of have hard real-time requirements. And there are many situations where you may need to do things really, really quickly that involve fractional precision numbers, and you just can't use floating point. So what do you do in those circumstances? Well, that's what we're going to talk about today. We're going to be looking at fixed point. Now, fixed point is this really cool idea that's been around for a long time and has been used in everything from, advanced computation before floating point was standardized up to things like games, and even when floating point was around and people just simply didn't have the hardware to run it fast, fixed point was a big thing. So let's take a look at fixed point math. It's really cool, I promise. It's actually really fun. Okay, so fixed point math. What I want to do is just first show you what this is, right? Fixed point, and then we're going to build a whole system for running it, right? I'm going to write a library. I'm going to write it in C, but you can write the same stuff in any language, because as long as you have integers, you can actually write this fixed point math system. And it's really cool. And if you're working on a microcontroller, and we'll look at some motivated examples for this later, then this is going to be a really great way of potentially accelerating your computations. Or maybe you've picked a chip specifically because it had a floating point unit and you knew you needed to crunch some numbers. Well, now maybe you can choose a cheaper chip because you don't actually need that floating point unit. Everything you need is likely possible in fixed point. So let's take a look. All right, first let's motivate this by understanding how floating point kind of represents numbers and why it's complicated versus how fixed point represents them. So I'm not going to go too deep into this. I've actually made a video about floating point quite a few years ago now, it goes into some level of detail. I think you'll get a really good idea about the representation there, but we don't cover all the complexity there, and we're certainly not going to do it today. But what I want to give you is a bit of a gist here. What we're looking at here is kind of the number line. In a way, only integers are shown, but what we have is that between all of these integers, we have a whole bunch of fractional numbers, right? Floating point performs this amazing magic trick. It's not really a magic trick, it's a very cool piece of mathematics, but let's call it a magic trick for now. It performs this very cool magic trick of being able to represent huge numbers and really, really tiny ones at the same time, and allows you to compute with both sides of that, right? So if you've got some astronomical sized number and you've got some quantum sized number, you can actually perform calculations on that same playing field. But that doesn't come for free, and we're going to see how that doesn't come for free in a second. This is what the number line in floating point looks like, kind of. It's a bit weird, right? What you see is that the numbers aren't kind of evenly spaced. And what you'll also notice is that we don't just count up normal integers here, we're doubling each time. The thing to notice is that in the first gap, we've got like loads of space for numbers in between 0 and 1. We can represent loads of them, tons of them. But when we come to represent all the numbers between 1 and 2, we have less space. We actually have half as much space for that. And that's kind of weird, right? What that literally means is that there are, in the floating point specification, half as many numbers in between 1 and 2 as there are between 0 and 1. And again, when you go between 2 and 4, right, and we've doubled that distance now, right, when we go between 2 and 4, now again, there's half as many. So as we grow the number in size, like the magnitude of the numbers we're representing, we are able to represent fewer and fewer numbers in between those numbers. This is what's called a logarithmic relationship, and it's kind of the trick to how floating point works. There's an internal representation where internally what is stored is kind of an exponent that puts you in a range like 0 to 1 or 1 to 2, 2 to 4. There's a representation inside that number that sort of says where we are range-wise, and then there is a fixed amount of bits dedicated to representing where exactly in that range we are. So that is kind of how floating point works at like a really high level. Here's what the trade-offs there are. Obviously, like, we don't have this nice linear relationship. Things can get weird if we're calculating somewhere in the middle of the range of numbers that we can represent. We don't have as much precision. There are all kinds of weird rules, and mostly it's just kind of expensive to do this kind of computation. You can imagine that sort of doing all the conversions between numbers down here and numbers up here, it kind of can get expensive. What does fixed point look like? Well, this in comparison is kind of a fixed point number line, right? And it's not, none of this stuff is really to scale or with the absolute real true values that you would see. But what we see is that between 0 and 1 and 1 and 2 and 2 and 4, we actually have the same number of numbers, right? Everything is evenly spaced. But we're not able to represent as many numbers, right? Floating point's got a trick that it uses to allow us to get huge numbers and tiny numbers using just like 32 or 64 bits, whereas fixed point, it doesn't allow you to represent such a huge range of numbers. But what it does let you do is represent all the numbers that you have in a certain range linearly with exact precision according to the number of bits you have. You can still get into the same problem like the 0.1 plus 0.2 equals not 0.3 exactly. That's just part of how computers work at the bit level. Like, we can't represent every number exactly, although there are certain things you can do in fixed point, at least in the abstract sense, that would remove that, right? Because, well, it doesn't matter too much for now. On an implementation level, that's not going to happen. What we do get to do in fixed point though, and this is really cool, is that we get to decide kind of what kind of range of numbers we want to represent and how much precision we want to have in between, right? How many numbers do we want to have in between each integer? We actually get to decide that in fixed point, and it's pretty cool because it allows you to choose for your application what makes sense, right? And where you're going to spend your computation. All right, all the computation is actually the same, right? It's really cool. You're going to see how this works, but it's one of the coolest, mind-blowing things about fixed point, right? If you're just doing numbers, if you're doing calculations on things like angles, right, and especially if the angles are in radians, then actually you're just really dealing with numbers from 0 up until 2 pi, or maybe some negative pi to pi, or some range like this, right? Negative 2 pi to positive 2 pi, if you want to have some sort of thing going on like that. But in any case, you're only dealing with numbers in this range. So what you could do is you could limit the sort of overall magnitude of those numbers to just, maybe like -8 to 8, +8 or something. Just a few bits dedicated to representing that whole part of the number, and then dedicate a whole bunch of bits to to calculating everything in between, right? The fractional values. It's pretty cool. Okay, let's get to an example. Let's put this in concrete terms. I've got a number here, right? This is a binary number. I'm not going to explain how binary numbers work now. I do have a playlist called the Bits and Bytes of Binary that explains like the real basics of binary and the operations and 2's complement and some stuff like that. If you're coming from zero, I mean, go and take a look at that. Otherwise, I'm going to assume you know how binary works. So this is an 8-bit binary number. This is what its unsigned representation means. That's basically if you add up kind of all the bit positions here, like you'd get the decimal number 156. If you took this to be a signed number, where of course this top bit is set, that kind of indicates this is a negative number, we get negative 98, minus 98. Okay, simple, right? What if we were to make a little change to this system? And this is going to be purely a conceptual change, right? What we have under the hood here is a data type uint8 or int8, right? Signed or unsigned 8-bit integer. That doesn't change. We're just going to play conceptually with a number here. What if I was to take these bottom 4 bits and move them over here, and then come and grab this little virtual point down here and put it in between? What we've done is we've decided that these top 4 bits are going to represent, just like in normal numbers, right? Just like if you have a number like 10.5, like this part represents the whole number, right? The 10 in this case. This is not actually 10, this represents 9, so it's kind of a bad example, right? This is 9 point, and then we've got something over on this side that represents a fractional value. And the number we actually have here is 8 plus 4, so we've got 0.12. But it's not actually 0.12, like in a decimal sense. This is actually conceptually 12 divided by 16, because we only have 4 bits available here to represent kind of all the numbers in between 9 and 10. So what we do is we take the value we have here and we divide it by sort of the number of values we can represent in this range, and then that gives us kind of the true value. So let's just pull up a terminal here, Python, and so what we've got is 12, we divided by 16, that's 0.75, so this number is 9.75 in fixed point. So that's pretty cool, right? I think this is awesome. Okay, so let's imagine, this is assuming an unsigned number, by the way, right? If this was signed, obviously this top bit is still set, and then that means that we would have to think about our number a little bit differently, but let's leave that for now, because conceptually it doesn't matter. I just chose to put this decimal point, or rather the radix point, as it should be called, I put this radix point in the middle of the number, but there's no reason we can't put it somewhere else. So if I take this point and I move this one over and I put it here, well, now all of a sudden what we have is 1, 2, 4. So we've got 4, and then the number that we have here is, this was 8, so 16 plus 8 is 30. Sorry, I'm really bad at math. 24 plus 4, so this is 28. So we do 28, and then we're going to divide it by not 16 but 32 in this case. So this would be now 4.875. That's pretty cool, right? That's what we get from this. I hope I'm doing all these calculations right, because I didn't think about them ahead of time, and I'm really bad at the mental math side, so I hope you excuse me if I do make some mistakes. Anyway, I think you get the point at this point, right? Basically, the idea is that we've got this virtual radix point. We can move it anywhere we want. As long as we know where we've put this point, we can sort of say, okay, these bits mean this, these bits mean this. Why is this interesting? Obviously, you could do this, right? Obviously, you can think about this, but it's not useful to just represent numbers. You actually also want to perform operations on them, right? If I can't add numbers together and subtract them and do all this kind of stuff, then what's the point? Well, here's the cool thing. If I add two numbers together that are in this representation, right, and they both have this point in the same place, if I add two numbers together, guess what? It just works, right? It just works. So the addition will come out to be the correct value in fixed point. Isn't that amazing? Isn't that just kind of mind-blowing? It makes sense if you think about it, right? Let's just sort of like move the number back here and say that we had a number that was all zeros, but we added these 2 bits here. So what we would do is we would get, or rather, let's say we got something that would roll all these bits over to 1 over here. So we would get all zeros on the side. So basically we'd be adding just the fractional part to shift us to the next number. It makes sense, right? It kind of makes conceptual sense. If you have zeros all over here and numbers over here, well, obviously you're just representing 0 point something. So if I add that to this, it shifts the next number up, right? All of these bits would kind of ripple carry, and then this would go up to the next value here, and we'd have 10 instead of 9, and that would make sense. So yeah, I hope you're with me. I hope that made some sense. It's just addition. The addition just works. And what we'll see is that things like multiplication and division, they almost work exactly the same as well. We just have to do a little bit of rescaling after the multiplication or division in order to sort of set us back in the right point, because those operations end up scaling you out of by a relationship with kind of this decimal point, radix point. Okay, that's it. I think we should actually get into the implementation now, because if we only talk about the kind of abstract, we'll get nowhere. Here we are in a C file, right? I've set up a little C project. It doesn't do anything yet, so if I just type hello in here, let's get out of Python. If I run make run, it will run it, and we get hello. Cool. All right, so we're ready to do some work now. Okay, where are we going to start? Let's actually start by thinking about how we formalize this idea of like setting our radix point somewhere, right? So first of all, what I want to do is I want to just define something here, right? So I'm going to define something that says this is our fixed point integer type. I'm just imagining here that we would be writing a library that we could use again and again. So the idea is that we would say what kind of integer type we're using, because we don't know. You could be using int 16, you could be using int 8, you could be using int 32. We don't know that, so we're gonna put this here. And common actually includes standard int, so we can talk about the standard integers here. So I'm gonna say that our floating point integer type is actually int 32. Okay, so that means we got 32-bit integers, right? But we still need to calculate that out. So this is going to be the number of bits that we actually have, and to calculate that, we do size of our floating point integer type, and actually to fixed point integer type, I should say. I'm actually going to make a type def here as well, and the type def is going to be called fixed point int t. And that actually is just going to be like what we passed here, so we can use that. Then we can use a nicer type name. Don't worry if you're not like super familiar with C. It doesn't matter that much for this kind of stuff. Basically, we're defining a fixed point integer type. And I realize I need to do this the other way around, like that. Okay, so now we've got this thing called a fixed point integer t. And it's actually just int 32, right? It's just a 32-bit signed integer. So how do we get the number of bits? Well, the size of this thing is measured in bytes. So this is 4 bytes, and we need to convert that to bits. So we need to multiply it by 8, right? There are 8 bits in a byte. And the way we can do that like efficiently is we can just shift it up by 3, and that will give us like a multiplication by 8. So this will come out to be 32 bits. All right. Now we're also going to have to define how many bits from this 32-bit integer we are going to give to the fractional part, and how many bits we're going to give to the integer part. So it's kind of conceptually, it doesn't really matter which way around you do this, but let's think about giving ourselves, and I want to do this in a way that kind of makes sense. So let's do something that doesn't quite go down the middle. Let's say we have let's call that num bits. This is going to be the integer bits, like the number of integer bits we have. Let's make this, I don't know, 14 integer bits. We have 14 bits dedicated to representing integers. So what does that give us? Well, 1 to the 14 is 16k, right? So we have 16k values, and if we're dealing with signed values, that means we have half that number, right? So we have around positive 8,000 and negative 8,000. This is kind of the range of numbers that we can represent if we choose this number of bits for our integer, right? And naturally, the number of fractional bits that we have, the fractional bits, well, that's going to be the number of bits we have total, so 32, minus the number of integer bits we've allocated, right? And it's actually kind of conceptually the fractional bits which are more important, but it doesn't matter that much for now. So let's just line everything up. We don't need to line everything up, but I just can't help myself. Okay, so now we've got our sort of bounds, right? We've got a type that's actually concrete and that's representing our values, and we've got these sort of definitions here. So the next most important thing, I think, is to figure out how we can, when we're mechanically working with this type, because we're going to write a whole bunch of functions for doing addition, subtraction, whatever we want to do. We're going to write a whole bunch of functions, and we're going to need to be able to access, you know, the fractional part or the integer part. So let's make some bit masks now to do that. So let's define ourselves a fractional int mask, or fixed point int mask. And what that's going to be is I just want to have the 14 bits on the top of the number, right? And if we think about this, how this will look. So 2, 4, 6, 8, 10, 12, 14. So we've got 14 bits there, 16, 18, 20, 22, 24, 26, 28, 30, 32. So this is kind of our bit distribution. So we have these 14 integer bits here. It's the int part, and then this is our fractional part, right? So this is our distribution. So if we want to build a mask, we want something where we have all 1 bits here and all 0 bits here. So we could sort of select the integer part. So how will we do that? Well, basically, to make a mask, you just you take 1, you shift it up by the number of bits that are interesting for you, right? So we've got 14 integer bits, and then you subtract 1. And if we look at that in binary, that gives us this, right? So that's going to be these 14 integer bits. But we actually need 14 integer bits on top, and then sort of, what's it going to be, 18 fractional parts on the bottom, right? So we actually need to shift this up by the number of fractional bits we have, which is 18. So if we shift this all up by 18 bits, we get this, and this is the mask we want. So what we want to do is we want to say 1, shift it up by the number of integer bits, minus 1, take all of that, and then shift that up by the number of fractional bits that we have. That's our integer mask. The fractional mask is a little easier, although it's pretty much the same. So it's 1 shifted up by the number of fractional bits, minus 1. But we don't need to do any other shifting because we actually already have that on the bottom, right? We don't need to shift it anywhere. It's going to be these bits. So that's that part. We've got 2 masks. So now we can identify the fractional part and we can identify the integer part. Now, one more kind of mechanical thing which I think is useful for us to be able to identify is just what is the sign of this number? Is this a negative number or is this a positive number, right? And this sign is just the sign bit, right? So this is not anything that unusual. The way we can actually get this is just, this is going to be the FP sign, And we'll make this kind of a macro. I'm doing macros here. We could make these all functions, but I'm just making macros here for kind of the mechanical part. So for the sign, what we need is the topmost bit, right? We just need to know if this bit is a 1 or a 0, and that's what this is going to return. Although I think it would probably be more useful for this to return a 1 if it was positive and a -1 if it was negative. So let's think about doing that. So for that, we actually need to figure out, like, how can we just take an integer, any given normal integer, and get it into this format? Well, it's actually really simple for integers. So I'm going to write a little function here, or macro. This is going to be a fixed point from int, right? So we're going to take in an integer. I'm going to call it a. And what we have to do with that is we just take a and we need to shift it up by the fractional bits. So essentially we're taking our value of our integer, pushing it up into this part. That's just what we would expect to do with it, right? That's the normal way of working with it. And this will, of course, only work if we push integers which are in our range, right? If we have integers which are not in the, which exceed 14 bits signed, this is not going to work. So we have to keep that in mind, right? We are working with a particular range, and if we exceed that range, then weird things will happen. Basically, we're going to shift this up by the number of fractional bits that we have. And just to make this kind of explicit, I'm going to call this the scale. And the scale is literally just the fractional bits. And then I'm going to call something called the scale factor. And that is the scale, or 1 shifted up by the scale, right? Let's just align all this stuff. Okay, somehow that one didn't go. Alright, so I'm going to use these instead of talking about the fractional or the integer, because I get confused with those and I've made mistakes on that before. So let's just take the scale. So we're basically scaling up our value a by the actual number of fractional bits that we have, which you can think about it conceptually makes sense, right? Like, we are just shifting everything up into that integer position. But you can also think of it conceptually as we're scaling it, the whole number up by a certain amount by doing this, right? This is basically a big multiplication. Okay, so this is how we can get a fixed point number from an integer. This makes sense. We're just putting a number here. Okay, so to get the sign of a number, and because I said that I want this sign to actually return to us either a fixed point 1 or a fixed point -1, what we actually want to do here is to say, define, this is going to be a fixed point value 1. And the fixed point value 1 is just fp from int 1. Then we're going to have a fixed point value -1. And that's just a fixed point value -1. So we're just getting numbers in these formats now, right? And we probably want to have just 0 as well. And 0, well, it is just 0, so we don't need anything there. Okay, so these are some of the values that we're going to use. We're going to add at least one more there, but we'll get to that in time. So what do we do here? We want to just check if the topmost bit, the 31st bit, if we're thinking from a 0 index position, the 31st bit, if it's a 1, then the number is negative. How do we check that? Well, we can, if we knew the type of the number, it would be really easy. We would just make a mask like this, and we would know that this would isolate the topmost bit. But since we are allowing the user to provide this type, effectively we want to do that programmatically instead, right? We know the number of bits in this type, so what I'm just going to do is to say 1 shifted up by the number of bits, and I guess we need the number of bits -1, right? So that's going to be 1 shifted up by 32 Yeah, so we actually want to go 32 minus 1, which would give us this. So this is now a mask that identifies the sign bit. So let's take that mask and AND it with our input number A, right? That gives us the sign bit for A. And actually, maybe what is a better way of doing this? Because we don't... No, in fact, I am going to do this. No, I'm going to do this differently, actually. What I'm going to do is I'm just going to shift A down by 31 bits, right? So if we were to take something that had a sign bit there and shift it down by 31 bits, we just get this bit 1. So let's do that instead. Let's take A shifted down by the number of integer bits we have, minus 1. That gives us our number, and then let's just make sure that there's only a single bit here. So that's what we do there. And then if that bit is 1, right? So if that bit is, if that bit is 0, then we want to provide a 1 here. And if it's not, we want to provide a negative 1. Okay, so this gives us the sign of the number. Like the magnitude, or rather the unit of that, right? So if it's negative, we get negative 1. If it's positive, we get positive 1. We can do something with that. Okay. All right. So let's... maybe I'm just going to break this up into 2 macros. Just to... Like, it doesn't matter for the code, but let's have the sign bit be like this. And then we can actually just take this macro here and use it like that. And then if we need to reuse this, we can reuse it. Okay, that's a lot of like mechanical stuff for not having built anything yet. So let's actually start building. Okay. What is really useful, I think, and we don't need to understand this right now, but the first thing we should probably do is just build something that's going to allow us to show what these numbers are in floating point, because floating point, we have all this formatting stuff, printf, to be able to show it. So let's do that. So let's make a function here. Let's make a function. We'll make a real function here. So this is going to return a float, and it's going to be... fixed point to float, right? So we're going to take in a fixed point number, and our fixed point number is this type. So that's going to be fixed point number A, and we need to return a floating point number. So effectively, the way that we can do this is we can sort of convert our number to a floating point number and then divide it down by this scale factor. And that probably doesn't make a ton of sense right now, but it's going to work. So let's just do this. A number will convert our number A to a float, and then we will divide it down by the scale factor. All right, and then to get a number from floating point into, so this is going to be float to fixed point. To get a number from float to fixed point, right, so we've got something like 1.2. What we actually need to do is to multiply it by the scale factor and then convert that to our fixed point type. So we do this, then we'll take A and multiply it by our scale factor. And it's just the inverse, right? You can see we're just doing the same thing here in reverse, effectively. Okay, so let's see if that actually works. Let's try a few things here. So first of all, what I'm going to do is I'm going to make a fixed point integer, call it A, and we'll get that. So that's going to be float to fixed point, and let's just make 42.5 in floating point, and from floating point into a fixed point number, and then we'll convert it back. So this is going to be A equals %f, and we will use fixed point to float. Let's just see if that works before we do anything else. So make run. I'm so sorry, I can't type. Make run. Okay, so I'm missing a semicolon. Easy stuff. All right, cool. What you can see here is that we get the exact answer, 42.5. That makes sense. I think that should make sense. I'll bump the screen up just a little bit to make that clearer. Cool. One more time. Make run, 42.5. Awesome. Okay, now let's say I want to make a fixed point integer b, and I want to make that using our other way, like from int. I want to make sure that this works. So let's say fixed point from int, which is just a macro, and let's do minus 42 here. Let's try that. Let's see what b equals. Cool, minus 42, right? Great, so that's working. That actually works perfectly. Let's do one more C that just gives us it's that, and it helps if we actually put this in like that. Okay, cool. This all works, and that's brilliant. That's awesome. So first things first. This is not the first thing. This is about the 12th thing that we're doing. Let's think about doing some operations on this number. That's what's important. If we can't do operations, we can't do anything. So let's try to make these numbers a little bit more interesting, and we'll do some operations on them. So let's make b minus 18.2, and c is going to be a plus b. What do we think that this is going to come out as, right? Is this going to come out as what we expect? Well, let's just run it. So we're basically doing 42.5 plus negative 18.2, and the result here is 24.2999. Is that what we expect? Yeah, more or less it is what we expect, right? And it's more or less what we would get if we did this in floating point. So let's just try that for a second. 42.5 plus negative 18.2. Let's actually see what we get in floating point, and yeah, it's exactly the same, right? It's exactly the same value. Now there is a limited resolution that we can actually see in the formatting, so it may be the case that these aren't exactly the same number if we were to compare them like exactly. But what we're seeing is that we get the same kind of result, right? We're getting a very, very close result. And we'll see that for a lot of things. So addition just works. Subtraction. Let's try subtraction. So we're just subtracting a negative number, so we're actually just doing addition here. So we're doing 42 plus. So what we expect, of course, is 60.7, right? So we get 60.7 with a 1 there. And we get the same thing in floating point, right? We get that same non-precise addition because of the things we talked about earlier. That's great. That's perfect. It's working exactly. Okay, so let's actually we've got addition. Let's do multiplication and division next. Okay, so multiplication is quite an interesting one. It actually works pretty much the same, right? If we just multiply two fixed point numbers and they're in the same scale, right? Two fixed point numbers in the same scale multiplied together will essentially produce the right result, only it's scaled up by a significant portion, right? That's the one thing there. It's actually scaled up, but it's just scaled up by the scale factor. So if we want to write a fixed point addition, a fixed point multiplication where we take in two fixed point numbers a and b, what we essentially need to do is a times b, and then we just shift the whole thing down by the FP scale. That's it. That's all we need to do. Only there is a little bit of a problem with this, and that is that this multiplication will probably, in many cases, go outside the bounds of the 32-bit integer. And this kind of makes sense, right? Because the 32-bit integer can represent a lot of numbers, but we're actually using all that space, right? Because we use the bottom bits here as the fractional part. So we know that these are going to be filled in, and we've got something up here. So if we're making use of numbers that are quite large or even relatively large, we're going to end up like blowing this up quite a bit. So this is why we actually need to provide a second type that I'm just going to call the XL type, which is a number that a type that can hold a larger value. So basically what we want is something that represents UN64 here. And then we'll just add that in here to our type definitions, and we'll just call it FP int XLT, right? These aren't the standard names, but this is the ones that I'm going to use. Okay, and so to do this, basically we just need to convert our A variable into this, and then B will also automatically get converted into this in the most efficient format using this whole thing. So this should work for us. So let's give this a try. Let's try multiplying A and B together. So that's what we'll want to do here. Multiply A and B. Multiply A and B. Okay, let's do make run. What do we get? So we should get negative we should get, at least in terms of floating point, negative 773. That kind of makes sense, right? It seems that we're not getting that number. So it may be that I've done something weird. Let me take a look at what I've done. Okay, so this is kind of obvious point, but I actually just multiplied the numbers. So it helps if we actually run our function here. So let's do that instead. All right, so we're going to run the numbers. Okay, and here's what we get. We get, again, exactly the same result, right? And of course, don't worry about the exact conversions. We just want to see that we're in the ballpark here, because there are going to be conversion losses between going between fixed point and floating point, right? If you look at the operations we're doing, float to fixed, we're kind of converting things and dividing them down. There are rounding factors in floating point. There are things that are kind of out of our control in the way that floating point does conversions. So let's not worry too much about that. But we do get actually an exact result here. So how does division work? It's actually exactly the same. It's the inverse of multiplication. That makes sense because that's what division is. But let's just quickly whip this up here. So if we want to divide A and B, what we would do is we would convert A to a larger value. We would divide it by B, and then instead of scaling it down, we would scale it up by the scale factor. Now, the only reason that we don't do this implementation specifically, and this does work, but the only reason we don't is because that we're going to lose a bunch of precision by doing this division ahead of time. So what we can do instead is just kind of like rejigger the math a bit and just scale A before we divide it by D. So we'll scale up A, then divide it by B, and this will actually give us the same result, but with more precision. And if that doesn't make sense to you, just like try it out. Look at the numbers, like look at the bits as you go through these processes, and see where we would lose or gain precision in this. It's quite an interesting exercise. So just take a look at that. But let's give it a try. Let's actually divide these things down. So let's divide A by B. Let's divide A by B here. And let's run it and see if that works. Okay, so we don't actually get the right result here. Of course, I've probably made another mistake. What we should get in terms of floating point is minus 2.3 something, right? That kind of makes sense. Look at the numbers. Yeah, that seems reasonable. So let's see where I went wrong. Oh, okay, I think I see what I did here. So what I should do is I should actually first convert A and then scale up the value. So I should do it like this instead. Yeah, I think this is now right. So what we do is we make sure that A already has the space to scale into because we make it a 64-bit integer in our specific case, right? We make it the larger integer size, then we scale it, then we scale it up by this number of bits, then we do the division. So let's see if that works. Make run. All right, cool. Now we get a very, very similar result. It's not exactly the same anymore, and this is one of the places, division is kind of one of those places where, yeah, we're going to lose some amount of precision. What I want to point out here, and maybe this hasn't been clear, but all of these operations, all of the multiplications, the divisions, the everything we're doing, is actually taking place in integer space, right? All of the things we're doing are integer operations. Now, the reason that's significant, and I hope it's clear, but I'm going to really underline the point anyway, like halfway into the video, super burying the lead. The reason this is important is because floating point operations are way slower than integer operations, right? A multiplication or a division, especially a division in floating point, is super slow if you have to do it in software. It can be even slow in the hardware. In most modern hardware, it's not going to be that slow in comparison, also because we clock our computers at like ridiculously high rates and we have super scalar architectures and all of that kind of stuff. But on a little micro, even if you have floating point division, it may still be way slower than what we're doing here, right? Provided, of course, you have an integer division unit. If you don't have an integer division unit in your CPU, it's very unlikely that you've got a floating point division unit. So this is still going to be faster than if you emulated floating point. So in any case, what we're doing here is we're doing computation on our numbers way faster than we could, right? And that makes sense in certain circumstances like embedded hardware. It also made sense to video game developers back in the day before graphics cards and CPUs with FPUs inside were really common. So this is why if you look at the source code for a bunch of old games like Doom, you'll find fixed point math implementations inside, because that was what made sense to use. It didn't make sense to use floating point because you needed to crunch a bunch of numbers really fast every frame. So yeah, that's why you'll see that. Hope that's clear. It's good to underline that point at this point in the video. Okay, so we've got fixed point operations, right? We've got our addition, our subtraction, our multiplication, and division. Those are the like your bread and butter operations. They're not the only operations that we need to do math, right? We also need other ones. We need complicated things like sine and cosine and e to the whatever power and logarithms and that kind of stuff. Those are important, but they're arguably less important, right? For a lot of, I mean, let's say for 80% of applications, we can cover them with this, right? If you're writing an embedded software system and you're reading an analog signal from the world, from some sensor, and it's got noise in it, and you need to filter out that noise, the way in which you filter out that noise is with additions and multiplications, right? You can create a low-pass filter using additions and multiplications. You don't need to get complicated operations involved in that. And of course, scaling things up and doing additions and all of this kind of stuff. Most of the time, these are the operations you need. You do sometimes need things like cosine and sine and all of those other interesting and fun trigonometric and transcendental functions, but we don't need them right now. We are going to look at those in a follow-up video, right? I'm going to cover an algorithm that works on fixed point math that allows us to compute sines and cosines using only addition and shifting. It's crazy. It doesn't even use multiplication. That's insane. But that's what we're going to look at in another video. So for today, we've got our base operations. I want to look at another set of operations which are really important, and they're going to be like the rounding type operations, right? We want to sometimes like round our number up and down to the nearest integer. We want to use floor to get the like clamp it down to the closest integer, or clamp it up using ceiling. So we have a bunch of these type of functions, right? And that's why I want to implement with you now. And the reason I want to implement those with you is because they're actually a lot more fun than these other ones. They involve quite a bit more kind of thinking. And you wouldn't imagine that, I think, off the bat. Like, oh, rounding, that's like really easy. But actually, rounding is a complicated thing. And I don't mean to scare you, but actually no one really agrees on how rounding should work in programming languages. They do it differently in different languages. Like, so if you just simply do a rounding operation on a number, you may find that same operation in Python does something different in JavaScript, does something different in C, right? It's wild, but there is no agreed upon standard about how rounding works. Of course, in floating point, there is a standard, right? IEEE 754, that tells you how to do rounding operations, but there do exist non-compliant implementations out there that do the rounding wrong, even just by accident, because rounding is actually kind of hard. All right, let's take a look at rounding. All right, the first thing I want to do with rounding, before we do anything else, because it's going to be important to some of the subsequent stuff we do, let's figure out how to get the absolute value of a fixed point number. What do I mean with that? What I mean is, if we have a number like minus 42.725, I want to be able to turn that into its positive representation. That's the absolute value, right? The magnitude of that number. And if I were to put in the positive number, I would just get the positive number. So how do we do that? So I'm going to just copy paste that skeleton here, and we'll just call this fp abs, absolute. It's just the absolute value of a single number. So what do we do here? Well, and I'm going to make an assumption here, and I think this is a very fair assumption. And if you're using this library in something where this assumption would not hold, okay, you need to know the details of that, because that's quite specific, right? I'm going to make the assumption that we're using 2's complement arithmetic, right? 2's complement representation for signed numbers. That's basically everything. That's basically everything in the world now. We've agreed that this system makes sense, but there do exist implementations of things that don't use 2's complement addition. One interesting non-2's complement computer out there is the Apollo guidance computer, right? Which was a custom-built computer for the Apollo missions. That used a different representation, right? It didn't use 2's complement. And so if you're looking at all the math there, and there's a whole bunch of math that happens for the Apollo missions, would you believe it? Like landing rockets and stuff on the moon. Not rockets, but you know what I mean. Landing things on the moon, guiding a trajectory of a rocket from the Earth to the moon, actually involves quite a lot of mathematics. So they had a lot of advanced mathematics happening on that Apollo guidance computer, but it wasn't in 2's complement. It's completely irrelevant and not useful for us right now, but I just want to put down that little tidbit here. Okay, so how do we get this number? The way in which you get a positive value, or rather the way in which you get the positive value from a negative value in 2's complement, is that you invert all the bits and you add 1. That will take a positive number and flip it into its negative number, so like 42 into minus 42, and vice versa. We only want to do this if this number is actually negative, right? Because if it's positive, we don't need to do it. So what we can do is we can say if the fp sign bit, and let's just look at the sign bit now, because we don't need to look at the anything else. If the sign bit of a, right, if it's 0, we just return a. If it's not, then we can return invert all the bits of a and add 1, right? This will give us the absolute value. So let's try that out. Right, we've got b. Let's try the absolute value of b. So that's going to be fp2 float and then fp absolute of b. Let's see if that actually works. Okay, so what we get is that b is negative 18.200001. Too many zeros in there. Absolute is the positive version of that. Great, that's awesome. And just if we were to make sure that b is, this works when numbers are positive, let's add that in as well. And what we see is when we get negative b, which is actually a positive number, it still comes out to the same thing. Great, that's great. What does this have to do with rounding? Well, the reason I've done some of this stuff is because when we do rounding, actually we need to think about which kind of, if the number is positive or negative, because 2's complement actually kind of like mirrors all of the numbers around, and it also will mirror our fractional part around. So it's going to get confusing when we start to think about whether to round up or round down. So that's why we're going to start with absolute. Let's go next to simply getting like, let's do something called truncation, right? Or floor. Let's call it floor, right? So the idea with floor is that we want to round down, right? Take a number, 42.7. We just want to get 42, right? Negative 42.7, we want to get negative 42, right? We just want to clamp it back down to its lower integer. And again, the rules for this are not actually agreed, right? You will find that there are different implementations of what this means. It's confusing. There's round towards 0, there's round away from 0, there's round to nearest integer. There's all this kind of weird stuff. All right, so let's do floor. It's a really useful one to have in the arsenal. So floor. You may think that we could just do something like this. So we could just do, say, we've got this thing, the integer mask, right? And that just removes the fractional part. So maybe we could just do that. We could just take the integer mask, fp mask a, integer mask, ANDed with a, and that would be enough. So let's try that out. And let's, we can get rid of some of this other stuff now, but let's do, no, I don't know what I did there, yep. Let's get rid of some of this other stuff here, and let's do floor of A, so that will round this one. And let's do floor of B, that's going to do a negative number. And we want to do this floor. And that's going to be A, and that's going to be B. Let's see what happens when we do this. Okay, I've missed something somewhere. Yeah. Okay, so what do we get here? Well, we get the correct answer in the positive case, but in the negative case, for some reason we're at negative 19 now. So we're like off by 1. And it kind of has to do with that whole 2's complement thing, right? You can see that we're also off by 1 here. We're adding 1. So if we were to add 1 to negative 19, we would get negative 18. So that's actually what we want to do effectively in a floor. We need to check if we're negative, then we want to add 1. So let's have a look at that. So let's first do that. If the number is positive, so we can just check if fp sign bit of A, if it's positive, then we will just do this. So let's just, let's do that, return. And if it's negative, then we will do the same thing. We'll just add 1. Right, this makes sense. So let's do make clear. Oh no, we don't want to do that. We don't need to do that. Make run. Okay, so, oh yeah, and of course we can't just add 1. That's a good point. I need to fix this in the absolute function as well. Oh no, I don't. In absolute, we're not dealing with the numerical value. Here we're actually trying to add fixed point 1. So if we're adding 1, we're actually adding a very small fractional value, right? Because this is a fixed point number. The 1 needs to be here in the integer part. So what we need to say here is to add fixed point value of 1. Try again. All right, great. So now when we floor A, we get 42, and when we floor B, we get negative 18. Awesome. So that's floor. What about ceiling? So that's going the other way around, right? If we are, well, in ceiling it's a little bit different. If we're exactly on the value, if we're exactly 42, then we don't round up or down, right? We just stay on 42. If we're 42.1, then we're rounding up. We're rounding up to 43. So that's something we need to take into account here. And this is going to be where we start to get another element involved. Because in order to figure that out, we kind of need to know, like, are all of these bits 0? That tells us, if all of those bits are 0, that tells us we have just an integer value, right? We don't have any fractional bits. So in order for us to to get to that, we want to be able to ask for the fractional part of a number. So let's do that quickly as well. Before we do ceiling, let's make a sub tour into the fractional part. So what I'm going to do is I'm going to say fp fractional, and we're going to take an a, and it's just going to give us the fractional part. So if we put in minus 1.5, we want 0.5, right? That's what we want. Not negative anything, just 0.5. If we put in positive 147.672, we want 0.672 to come out, right? Just the fractional part. Don't care about the rest of the integer, don't care about the sign, none of that. Okay, so how do we do that then? Again, you might think, naively, we could just take our number, a, and it with the fractional mask, right? That just gives us these bottom bits. So let's try it out. So let's call this frac. So now we're going to look at the fractional part of a and the fractional part of b. So make run. Okay, so in the top case, we get 0.5, expected. In the bottom case, we get 0.77799999, so effectively 0.8. So we're sort of like inverse, right? We sort of have 1 minus this number, and it comes back to this idea that in 2's complement, the negative half is a mirror, right? It's not actually, it sort of runs the other way to what you expect. It's not like when you roll over the halfway point, you start going into negative numbers. You go into negative numbers, but from the other end of the number line. It's a little bit confusing. Watch my video about 2's complement if it doesn't make sense. There's an intuitive kind of circular representation that I like to think about. Anyway, hopefully it will make you understand this. So what we have to do is we have to do something different, again, if we are negative to if we are positive. So let's bring in this if statement again. If the sign bit is 0, this will work. Awesome. If the sign bit is not 0, well, kind of the easiest way we could think about doing this, and in fact, the easiest way we could do it without necessarily bringing in an additional statement here, is we could just take the absolute value of this first, right? We've got the absolute function. So we just make it positive first, and then we just get the fractional part, because we don't care about if it's positive or negative, but we do want it to come out with the correct value here. So let's try that again, make run. And what do you know? We got it, right? 0.2, not actually necessarily exactly representable in fixed point, so we get a little bit of error here, but that's great, that's fine. That's awesome. Okay, so now we know how to get the fractional part of a number. Now we can implement ceiling. fp int t. And that's why am I not copy pasting stuff? Okay, so what we're going to do here to get the ceiling is effectively we want to get the fractional part first. So let's do that. The fractional part is fp frac. If the fractional part is 0, then we can just return the number as it is. We don't need to make any modifications to it. Awesome. As it turns out, by the way, that 0 is the same even if we sort of do this inversion thing, so this was sort of slightly unnecessary, but in any case. Then what we can do is, if we know it's not, right, if we know that the value that we've got has some fractional part, we know we want to do this ceiling operation. So if it's 17, we want to go up 17 point something, we want to go up to 18. If it's negative 17 point something, we want to go down to negative 18 point something. Negative 18. So what we can do in this case is we can simply do the floor operation. So we can return fp floor on A, and then we need to just add 1 to it. But we need to add 1 in the direction of the sign, right? We need to add 1 if it's positive, we need to add negative 1 if it's negative. So how can we do that? Well, way back when, we wrote this fp sign bit macro that fp sign macro that says if we've got a number that's positive, we get positive 1. If we get a number that's negative, we get negative 1. So let's just use this macro. So we can do fp floor plus fp sine of a. So let's try that. Let's do ceiling of a. Make run. Okay, so what do we get? We get 43 in this case. We get negative 19. Both of these things make sense. Although what I want to do is also to check that if we were to do this on, say, just 42, or just negative 18, that case is also covered. Right? Because we don't want it to do any weird additions if we're already on a number. And yeah, that seems to work correctly. This is great. This is awesome. So the final thing that we have now is just the round operation. And the round operation, the way I'm going to implement it, and the way I think a lot of other places implement it, but not some others, is that if our fractional part is greater than or equal to 0.5, right? If we are basically on the halfway mark or just going above it, then we're going to round up, and otherwise we're going to round down. There is a big discussion about rounding. If you want to leave me comments on what your really in-depth opinions about rounding are, I mean, of course you can do it. I've looked into rounding, so I know what you're going to say as well. So I know what you will say in response. I just want to implement something. So this is what I'm going to implement. Let's do that. FP round. We're going to round up or round down. So I'm going to add in one more thing here, right? So we've got 0, we've got the value of 1, we've got the value of negative 1. I want to add in the value of half, right? So just 0.5. So we could do this using the from floating point number, right? We could do that. I don't want to do that. It's not necessary. And also we can't do it as a macro. Well, we could, but we just have to call that number every time. And the point of having this is that it's hard coded. So how do we get half of the number? Well, half is actually just when this top bit is set and all the other bits are 0. That's what half means in terms of like the bits. So this would be a 1, everything else would be a 0. How can we do that? Well, if we know how many fractional bits we have, we just take 1, we shift it up by that number of bits, which would put it here, actually in this place, and then we shift it back down by 1. Or we could also say we take 1 and we shift it up by the number of fractional bits minus 1. So let's do that. Let's implement that. Let me just show you it first, by the way. So if we go into Python, like if we had, let's choose 16, because like if we do 1 shifted up by 16, no, it doesn't actually matter. Let's do it this way. So we have 18 fractional bits, right? And I'm saying that if we do this, this is actually going to represent a half. So let's put this in our binary conversion. Not minus 1. 18 minus 1. Okay, how many bits do we have here? What is the length of this? The length of that is 18, so that we have 1 bit here and then the rest. So let's literally just do this. That gives us half. I hope you believe me that that is halfway in the range. It should make sense if you understand how binary works. So grant me that one. So how do we do this? We take our 1, we shift it up by the number of fractional bits minus 1. That's it. That's our value of a half. So now in the rounding operation, what are we going to do here? Well, we're still going to grab our fractional number, right? And what we're simply going to do is we're going to say if the fractional part is greater than or equal to the value of a half, then we're going to round up. So return FP ceiling of A. Otherwise, we must be rounding down, right? So then we'll just return FP floor of A. Let's see if this works, right? We've got something. Let's make a couple more numbers here. We're going to need some, so let's get rid of C because we don't really need C anymore. Let's add another C. That's going to be 18.5, 18.6, and maybe 18. 0, B, C, D, E. Let's just do negative numbers first, and then we'll do positive numbers afterwards. So let's do it like this. So we're going to have the round of A. It's actually not of A anymore, it's of B. And then we've got the round of C, D, and E. Let's see what happens when we round on these numbers. Okay, so when we do a rounding operation on B, we get 17. So that's not right. Something's going wrong there. Now I'm wondering what the case is there, because if we do ceiling and we have an exact fractional number of 0, then we should just return the value. So I'm surprised to see that we get 17 here. And I'm tempted, in fact, to put down a breakpoint and see what the path we're taking is. So let's do that. I'll put a breakpoint in the round function, and I'll fire up the debugger, and we'll just see what we're getting here. So what's the fractional part? It should be 0. It is 0. So if the fractional part is greater than or equal to the value of a half, this gives us the fractional. Yeah, so if it is, then we would do that. It's not, so we're going to floor A, sure. And in floor, we're looking at the sign bit. Okay, and here, of course, we don't have this guard. We don't actually have the guard. And the floor, so we should just put this in, right? The same thing. If the fractional part of A is 0, then we don't do any of this stuff. So let's do that, because we need that same operation. Let's stop the debugger. If the fractional part, then we'll just return A. We don't need to do anything there. So let's see if that resolves our problem. Make run, and somewhere I've missed something. Implicit declaration of fp frac. Oh yeah, fp frac is defined after, so let's just put it above. I mean, in reality, all of these things would be library functions, so they wouldn't really matter that much. But okay, so what do we get? Let's have a look. In the case of negative 18, we get negative 18. That's good. In the case of negative 18.2, we would expect to round down, right? That makes sense. So we're rounding towards negative 18. So we get that. 18.5, we round up, so we go negative 19. And 18.6, we also are above, so we go to negative 19. And, you know, if we go into Python and we use the round function and we say negative 18, we get negative 18. If we do negative 18.2, we get negative 18. If we do negative 18.5, well, here we just get also 18, but if we make it 5, 1, then we get 19. So in the case of, I think this is a case of even and odd. So if we were to do this in negative 19, it would round. So that's a thing with rounding. If you round differently on even and odd numbers, there's a good reason for doing it. It's like half the time you round up, half the time you round down. It gives a better distribution. I'm trying to keep things simple here, as simple as possible. So that's why I didn't implement that. But you can see that this basically works the same, but differently, but the same. Okay, so that's good. I'm happy with that. Let's actually just do this on positive numbers as well, just to have some assurance that it does work. And I'll just keep it to the same magnitude. All right, so make run towards 18, towards 18, towards 19, towards 19. Awesome. That's fantastic. Okay, I think this is all of the operations that we need to implement. We don't want to go crazy here. Let's do one motivating example. Let's think about in terms of microcontroller now. Like, what might we want to do with a microcontroller? So one thing, and I alluded to this before, one thing we want to do is we want to read analog signals from the outside world through the analog to digital converter that lives on board the chip, right? This is a very common thing. This is like the basis of embedded software, essentially. We take analog signals and we turn them into digital, and we do processing on them, and then we do stuff, right? We turn motors and actuate actuators, right? That's embedded software. So let's think about an example. So my example is going to be that we've got an ADC on board, right? And the ADC is 12 bits. So what this means is that we sample analog signals, and they come back to us in the form of a 12-bit number, right? So that means we get 0 to 4095, and we have 4096 total values, right? 12 bits. Very common thing. It's also common to have more bits, but this is it. This is what we got, 12 bits. Now, let's say in our imaginary microcontroller, which could be this exact one, right? That the analog reference, like the reference voltage that we're dealing with, is 3.3 volts. What this means is that a value of 0 volts is going to be a value of 0 in the digital system. And a value of 3.3 volts is going to be 4095. And this is going to be linear, right? So there is a linear mapping from 0 up to 4K that maps from this 0 to 3.3 volt range. These are all constants that we know ahead of time. So, how can we do something with this? Let's imagine we're writing some C code for a system where we're getting these analog voltages and we want to do computation with them. We want to do this computation in fixed point. Normally in the datasheet, and of course you can just derive this. If you play with the numbers, it makes sense, but you can derive how the mapping works, right? So normally you'll get some calculation that says, okay, well, you're going to get a number in this range. And so you're just going to divide that number, like, let's think about it like this. Let's say I've given you the number 4,000, right? Something really close to 3 volts, 3.3 volts. So let's say we divide that by 496. That gives us something that is almost 1, right? But this is going to give us a number between 0 and 1, and we're going to get really, really close to that number. I guess we should divide by 4095, right? Because that would give us 1 in the case that we had that. So we've got this number 4000. So if we now multiply this number by our reference, 3.3, we get that our voltage that actually went in, that represented by this number 4000, was 3.22344, a bunch more numbers, right, with precision, right? And of course there's precision loss, there's noise in the ADC, so like at some point these bits, they probably don't mean much. It may be the case that they do mean something if you've got a very, very accurate amplifier and low noise system, but okay, forget that. So this is kind of the calculation you would get, right? You're going to like divide this number down and you're going to multiply it by your reference voltage, and normally it's just kind of assumed you do this in floating point, but of course we don't need to, right? Because we know we can make a constant floating point integer here, which is going to be our ref voltage, or reference voltage. That's going to be, we can just do float to FP 3.3 volts. So we don't actually need to do this thing in floating point at all, right? So instead, what we could do is to simply compute this ahead of time. And we know all the detail, right? We know the value we're trying to compute here, 3.3, and we know all the details about our fixed point implementation, so we can just compute these numbers ahead of time. No floating point calculations necessary at runtime. So what do? Well, take something like Python, figure out that we know that we have this, in this case, we have 18 fractional bits, so 1 shifted up by 18. this is our like maximum number. And if we take the reciprocal of this, like 1 divided by this is like the smallest, like this should represent basically 1. If we invert the whole thing, this now represents like what like a single bit would be in this whole thing. So if we want to take this and we try to take 0.3 and divide it by this whole operation, that gives us this value, 78643.2, right? We throw away the 0.2. This is now our fractional precision part. So the main part, the integer part, that's just 3, and we take on number 3. We know how to get a number from an integer. We take on number 3 and we shift it up by the scale, which is the number of fractional bits we have, which we know is 18. So we all those two things together. This is the fixed point number, right, that represents it. And we can, sort of go through this FP to float operation, and we can see the reverse of that. So if I take this, make it a float by just giving it a 0.0, and then we just divide that down by our scale factor, which is 1 shifted up by, where's scale factor? 1 shifted up by our fractional bits. So 1 shifted up by 18. What we get is 3.299999, a bunch of stuff, basically 3.3. So this number, we could just take this and we could pre-compute it and we could stick it in here, and this would work perfectly. This would be our 3.3, right? I'm not going to do that for now because we don't need to do it, but let's just keep in mind we could pre-compute that. Great. So you could run a script to pre-compute all your constants and populate them, or you could just eat the floating point calculations in the startup procedure. It really depends on your application, right? If you have critical stuff that you cannot do any floating point operations, then okay, pre-compute everything you can. Otherwise, this is a methodology. All right, so we've got a reference voltage, and we know how to get our number, right? So we've read an ADC reading. So let's say our we're going to get an integer value. It's 12-bit, so it's a 32-bit integer, but it's 12-bit. We're going to get an ADC reading, right? And let's say our ADC reading was 3,185. That's the value we got given this time. And we need to convert this into a fixed point number, right, that represents something between 0 and 3.3, because we want to work on the voltage values, right? These voltages are meaningful in the real world. The digital numbers are not that meaningful, but we need to do this conversion. So what do? Well, just the same calculation, right? So we take integer 32, or rather we should do this with our floating point integers. What we want to do is convert, first of all, this reading into the number. So what we can do ahead of time is we can just we need to do a fixed point division. So we're going to take our fixed point number, which is going to be our ADC fixed point. And how do we do that? Well, we know how to do this from an integer, so we're just going to plug our reading in here. Again, being careful that this actually fits, right? We've got 14 integer bits, and this is a 12-bit number. So just think about, like, if those two things were like the other way around, we wouldn't be able to do this. Just keep that in mind. Like, you need to be able to represent this. Of course, otherwise there's other ways of doing it. So we get our fixed point ADC reading, and then to actually get the like the real voltage, what we need to do is to take our fixed point reading, or our ADC reading, we need to divide it down by this whole 4095 value, which also needs to be a fixed point thing. So let's make another constant fp int t, and this is going to be the ADC max. Right, so this is the maximum value we could read from the ADC. Is this one, 4095. That's the maximum value we'd read from the ADC. So that is going to be ADC max. So we divide our reading by our max. Well, we know how to do that. Floating point division, fixed point division of this number by ADC max. And then we take this, which now gives us a number between 0 and 1, and we multiply this by the reference voltage, which we already have here. So we're just going to do an FP multiply of the reference voltage by this normalized value. And now we've got the real voltage. So let's have a look here. Let's do a printf. So the real voltage is going to be this. And we'll see if this makes sense, right? Let's see. Make run, 0 volts. That doesn't make sense. That doesn't make sense. So what went wrong here? Okay, let's try and figure out what went wrong. So I'm going to just shove a breakpoint in here, and we'll dive through the code until we can figure out where it went wrong. Okay, so the reference voltage, yeah, that looks about right. I think that's more or less what we had in Python. Maybe I can even scroll back that far. I can't. But that looks about what we had. Oh, it's here, of course, yeah. So the reference voltage here is 865075, and yeah, it's exactly the same. So that's what we computed. Awesome. ADC max is this number here, which I think makes some sense. So if we were basically to take this number, take this number and shift it down by 18 bits, we would get 4095. So that's correct as far as I can tell. So that's good. Then we got our ADC reading, which we're also going to plug into the same world. So we get our ADC FP. So we take that, shift that down by 18. Yeah, it looks right. And then we're going to do the division. So that's this by this, and then the multiplication. So let's go into the division first. We're going to make A into a larger integer, shift it up by the scale, and then divide it by B. So let's just see what the resulting operation there is. I'm not sure if I can plug this all into the watch window here. Not sure if this will work. No, because it doesn't know about the scale. So let's just say FP scale is 18. So we would end up getting this, this number. All right, so that looks about right. And then we're going to, we get this in the end. Oh, this is really, really silly mistake. This just needs to be converted into a float. So that's going to be FP to float. Okay. Try again. Okay, so that looks about right. I mean, I'm just eyeballing it, but yeah, that seems approximately right. So if we were to just do the same thing in Python, we would take this number, divide it by 4095, multiply that by our known reference voltage, which was 3.3, and that actually should be a division. And we get 2.56 with a bunch of repetitions, and here we get 2.56 with 3 repetitions and then 0.54. So we're really close. Keep in mind, this is not single precision floating point calculation. This is a double precision floating point calculation. So there's a whole bunch of extra precision in the middle, but this is awesome. This is actually exactly what we would expect to see. So now you can imagine that we're in a position where this is all we need to do, right, each time to get our voltages in. Then if we were doing a filter or something like that, right, you know, I'm not going to go into the details here, but like a low pass filter is just, it's something that looks like this, right? You take your new value and you take some portion of that value, right? So some proportion of that value, say 0.98, and you add your old value multiplied by basically 0.98, well, 1 minus 0.98, so 0.02. And this is kind of this is like not the order you would really expect this in. Something like this. And then you would say old value equals this. So this is a low pass filter. So you can see all we need to do is like multiplications and additions. and then we can filter our signal. Obviously, these constants, you compute them, right? You work out what the characteristics of the filter you need is, and then you put them into your program. You don't just like eyeball them, although you can for a lot of stuff, right? If you just need to like smooth something out, you can just sort of, most of the time you could do something like this, and you know, that will smooth it out. If that's all you're looking to do, if you actually want to perform real filters, then you need to calculate the parameters. Anyway, this has been our quite in-depth, quite long, so if you stuck with me to the end, thank you, quite long explanation of fixed point math, which I personally find really interesting. If you've made it this far, you're going to love the next video. The next video, we're going to dive into how do we compute some more complex functions, like sine and cosine, because of course, we need those sometimes, right? And there are many ways to do that, and we'll look at one particular explanation in the next video. If you're a patron of this channel, right? This channel has a Patreon. It's linked below. If you are a patron of this channel, what I've started doing recently is to make an additional video on the side for supplementary purposes. And if you're a patron, you can get that one very soon after this video is released. Those videos will sometimes be a slightly more in-depth explanation of what we've done. Certainly not today, because we did a very in-depth explanation. But something that's along the side, right? Some of the side quests that I've come across while getting to this point, maybe some interesting like related thing that is not directly impacting the main video, maybe some extra detail. It's this kind of thing, right? So if that's your jam, right? If you find this channel interesting and you're thinking, I'd like to have some way to support the channel, keep the videos going. You don't have to support me financially. I mean, if you're in a position to do it, it's fine. It helps me buy equipment for the channel and things like that, but I'm not going to starve otherwise. So, I mean, only do this if that's something that you're really interested in, supporting this kind of content. Otherwise, if this is your jam, you might want to become a patron, because you'll get these extra videos where we just go a little bit more in depth. Hope you enjoyed this. I've really enjoyed making this this video and getting to all the mathematics. I'll see you in the next one.